Hello and welcome to Technical Utkranti, and today we'll be looking into the third question of binary search. But before that, let's have a look at the thought for the day. Alright, so we have done two videos as of now in binary search, and this is going to be the third video. So what is the question? You are given an array in which all elements occurs twice except one element which occurs just once. We need to find that one element which occurs just once. For example, if this is the input given to you, then you know 2 is the answer. We can do this question simply using linear search. That is the O of n based approach. Now, we have a binary search based approach also, which takes log of n into log of n time complexity. If we take large values of n, then we can see that this would be faster. All right, so let's understand how are we going to do this using binary search. We know that the number that we want to find is coming just once. All right, and all the numbers are present twice, which means this is the only number on left of which there will be even numbers and on right of which will also be even numbers. All right. And when I say left, I can also say less. And when I say right, I can also say greater. Now let's understand the code. What we are doing, we have the array sorted. So we have low and high pointers as the minimum and the maximum indices, and count is set to true, which would serve as the indicator where we need to stop the while loop. We calculate the mid index and the number at the mid index. Whatever is the number at the mid index, we see how many elements of the array are less than this particular number. And if those elements are even, then there does not lie our single occurrence element, right? Similarly, we see how many elements are greater than this number. If that also comes out to be even, it means that of this number, on the right half of this number also, we don't have that single occurrence element. It means that this number is that single occurrence element. And we set count to false and return. In other cases, where we do find that number of elements less than this number are odd, then we reduce the search space by setting high is equal to mid minus 1. Similarly, if we find that the number of elements greater than this particular number are odd, then our answer lies on the right half. And so we update low to mid plus 1. And our binary search continues. Let us look at one of these functions, that how are we calculating the number of elements in the array that are less than this number. So we have this function over here. Comp becomes nums of mid. So remember, when we say comp here, we mean the nums of mid. Okay, we basically need to find how many numbers are less than comp. Here again, we apply binary search. If the number at the mid value is less than comp, then it means that we can have more number of elements that are less than this particular value. So we increase the value of low pointer. When we see that the number at the mid value is greater than or equal to comp, then it means that we need to reduce the number of elements that are less than comp. So we set high is equal to mid minus 1. Finally, after this low less than equal to high relationship is false, the low pointer would point to the number of elements that are less than com. Let us look at it with the help of an example. We have low pointer as 0, high pointer as 9, and we have said comp is equal to 3. Okay. Now let's apply binary search. 0, 9, we get MD, mid as 4, and nums of 4 is 3. Okay. Is 3 less than 3? No. Which means that we need to decrement the high pointer. Correct? If this particular number, nums of MD, which is 0, 1, 2, 3, 4, if this number is not less than comp, then it means that we need to further reduce our search space of numbers that are less than comp, correct? So we'll do high equals to mid minus 1. We'll calculate mid value and nums of mid comes out to be 1. It means that we can increase our search space of numbers that are less than comp. And hence we set low equal to mid plus 1. We get mid of 2. Nums of 2 is 2. 2 is less than 3. 2 is less than 3. It means that we can have more numbers that could be less than this particular comp. So we again set low equal to mid plus 1. And we have low and high equal to 3. So low is here as 3 and high is here as 3. Over here we have found that these many elements are less than comp, and over here we have found that these many elements are greater than comp, right? What about this index? We see that at this index the number of elements are not less than, so this element is not less than comp. It means that high will go this side to reduce the search space. But in doing so, high becomes less than low and our binary search is done. And what does low indicates? See, to the left of low are all the elements that are less than comp, right? So since low is 0 indexed and low is 1 ahead of this search space, so low would point to or low would indicate the number of elements that are less than comp, right? Okay. This is first case. Okay, the second case I just would like to indicate is the case when low and high are equal and low moves this side. So when would low move this side? When this particular condition is satisfied, right? It means that this element had it been, let's say, 2, so this element is also less than comp and low moves ahead, low pointer moves ahead, and then it would become 4. इसको नहीं रखना है, ठीक है? So I hope you understood this part of the algorithm also, and the similar implementation is there to find number of elements that are greater than comp. So at the end we'll return nums of mid. Let's submit and see if we can submit if our answer is acceptable or not. So if the answer is acceptable, and I hope you understood the question, the approach, and the solution. If you did, please give it a thumbs up and subscribe to my channel. Thank you. Bye bye.